So you don't have any questions till now? Everything is okay? In the lectures, homeworks? No? Okay. Okay, today we are going to talk about phase transitions, and we are going to do three things. We are going to discuss van der Waals equations. We are going to do an exercise on Maxwell construction on van der Waals equations. And we are going to do an exercise of the exam. Okay. Who can tell me what are phase transitions?
Like from liquid to gas.
Exactly. It's a sudden change in the physical and chemical properties of matter. And a good example is liquid from gas. We can see it in the kitchen. Water to ice also, but there are way more. And the way to characterize them is that they gives free energy. Per particle. It's the same in both sides of the phase transition. Okay, and also the chemical potential is the same in both sides. You can see also phase transitions in you can understand chemical reactions like phase transitions. It's also very interesting. Okay. This is a very important topic in physics in general. There's a lot of research going on with this. So generally, this is the first time, like the first lens you're going to get. But if you continue with advanced studies, you will see way more things about phase transitions. You saw with Stas today the van der Waals equation, right? Okay, do you recall the equation for the ideal gas is something like this, right? So this is very similar. So the idea of the van der Waals equation is to do a correction on the pressure, which is led by this parameter A, which is an attraction between molecules. And the other thing that changes is that we change the volume here, right? By a factor B. So the idea is that these particles are no longer just points in the space. These are like spheres. So they have their own volume. So we are saying, okay, so the total volume of the thing is the total volume without the volume of the particles themselves. Okay, and you also saw this diagram with Stas, right? Where he showed you that at some point on the PV diagram, Like you have these curves, and then at some point, something like a bump happens, right? So the idea is that we know from stability, like for knowing that D is like the entropy is always a monotonic increasingly function of energy, a number of particles and volume, right? Like it's always growing. We know that this must be true. That is that the derivative of the pressure with respect to volume must be bigger than 0, right?
Smaller.
It must be smaller, right. In general, this happens, right? Here, in all these sections of the curve. But there's a problem that here there's a section where this doesn't happen, right? And this is not physical. Do you know what the meaning of dp of dB being greater than 0 means? Like the gas can always win energy by being more compact, like decreasing the volume. If it decreases the volume, then it gains energy. So if you have a cup with gas, let's say, with air, then the air is everywhere, right? But if this was true, then the gas will start compressing and putting all the particles just in one point, and there will be no gas here, and that's not physical. Like, that's crazy that the gas will just suddenly decide to arrange in the half of the glass. So that's the reason why, and that's the meaning what compressibility means. Like the gas, a gas that wants to compress itself, it's not stable mechanically. It always can do it. It will do it, and therefore it will lose. Like it can lose energy from a process like this. So it will always get slower and slower, and there will be vacuum here. And we have never seen anything like that in real life. Okay. So that cannot happen. The other idea is that something terribly wrong with our theory is going on. Right? We know that our mathematics are saying us that something is weird, and the idea is that we are undergoing a phase transition. We are changing gas. We are going from gas to liquid. And we want to understand the properties of the system when we cross from this phase to the liquid phase. How do we do that? You know, how, like, what are the conditions that have to be done, be met?
Colder?
Hmm?
When it's colder, you mean?
Okay, so you have to be in lower temperature, but you can also, like, we have a mathematical description, and it's that the first derivatives must be 0, right? So if it's a first order phase transition, then dp
Then the second derivative must be greater than 0.
is 0. That is true, like in another system, but this is for like, and also the second derivative is 0.
The second derivative
Is also 0.
no.
When this is met when we have second order phase transition. Okay. Okay, this is very important. Like here in our Maxwell construct, like in our van der Waals equation, this happens. like there's a point where it's just here in this diagram. Let me draw it in another color. We have these regular curves, and then it suddenly like does something like this, but it actually doesn't generate a bump, like an up and down. And this is the second order phase transition, because there is no like sudden jump. And a first order phase transition is something like this, and this whole area for a first order phase transition is not physical. Like the theory doesn't, like this doesn't agree with any experiment. Okay. So what can we do about it? Okay, so the Maxwell construction is it's a way to deal with this. Okay, the Maxwell construction, it's a way of being honest. It's saying like, okay, here like in this region I cannot say anything. Can you see here, or should I? Okay, here I cannot describe anything. My theory is very, very bad of describing what I see in experiments. But what I can surely do is that I can take this point and say from here and here, it works. So instead of taking this weird curve, I will only take a line. And the physical interpretation of this is just saying the energy required to usually to expand, like if I decrease temperature, then I will expand the volume. But here what happens is that I have a sudden phase transition. The energy is going to changing the physical nature of the object that I'm looking. Okay, so it's going to compress to not to compress to expand. It's going to expand at this like low temperature, like without showing any growth in the pressure. Here I have a gas, right? Here. And then I start growing on pressure, and suddenly it goes to something very compressed. So then I start having a liquid. Okay, that's the idea. Like all the pressure usually going to compressing the liquid is actually going. It's actually going to change the matter. Okay. Is that clear? Like the idea is that instead of using the pressure to compressing the volume, the gas, well, in this part is liquid. Instead of going to compress that, like that phase, it's going to change the way the thing is itself. You're making a transition from something to something different, and there's where all the pressure is going, and then you're going like you change the matter, and then the equation works perfectly. Okay. Okay, and the way of saying that is that it's approximating this curve. with a rectangle, right? This is what we just did here. Instead of saying that I have a curve, in this point, I have a straight line, like a constant line, okay? That's what I'm saying here. This is a constant, and I am just taking the edges to value the size of the box, okay? Okay, so let's do an exercise to see how this works. Okay, first we want to find the critical temperature. Do you have any idea of how we can do that? How we can find the critical temperature? Okay. The way to do it is that we need to satisfy these two conditions. Okay. The derivatives, the first derivative and the second derivative must be 0. So let's do that. So dp from dv. Okay, so let me write first the function. So the first derivative of the pressure with respect to volume is just by the way, this little b is just the regular volume divided by the number of particles. Okay. So this is the first condition, and this is the second condition. Right. Okay, and now, okay, so then what are we looking for? We are looking for the temperature, right? So this is easy enough. Like we can substitute this equation into this one, right? And then, like, we have two variables, which are the molar volume and the temperature, right? And we have these two equations. So we can solve for the volume here, let's say. And then we have that the volume is 3 times V. So this is what I told you. Like the volume per particle is 3 times V. And using this result and plugging it here, we get that the critical temperature is 8A over 27. Okay. Did you hear any questions of how we do it? Like how did we get this result or anything? Is that clear? Okay. So the second part of the exercise is to find, using Maxwell construction, we need to find how the volumes in the two phases relate between each other. Like we want to derive a mathematical expression that tells us if we know the volume in the liquid phase, then we have the molar volume in the gas phase, and the other way around. Okay. Oh, of course, this makes only sense on equilibrium, right, between the two phases. Okay, so how do we use the Maxwell construction?
The pressure in equilibrium.
Okay, the pressure in equilibrium is the same. 2 times the volume, right? Right? What we are saying is that we are assuming that the pressure is constant, so we can just plug in like if it was a straight line in the graph. Okay, but we actually know what pressure is, right, from here. So let's go grab that. Okay. The first integral is just a log, right? And this is just lowering the exponent here. And from here we have this. Okay, so 1 second. Let me just put this in. This would be R. Okay, do you agree that this, like, I evaluated only in the molar volume? Okay. Then we also know that the van der Waals equation works perfectly in both sides of the curve, right? So when we are not at the equilibrium, we can just write that the pressure, like, a way to say that is that if we approach from here, we have an expression for the pressure, and if we approach to here, we have an expression for the pressure, but here it depends on the liquid, right, in the molar volume of the liquid, and here it depends on the molar volume of the gas. So the pressure at equilibrium it's like this. Okay, so this is the, we have these two equations. This is for the liquid phase. This is for the gas. Okay. Sorry. Okay. And then we want to relate we want to have a relation between the molar volume of the gas and for the liquid, right? Okay, so how do we do that? So we have three things that we don't know. Okay, we don't know the pressure at equilibrium, we don't know the molar volume of the liquid, and we don't know the molar volume of the gas, right? But we actually have three equations, so actually we can solve this. This is one, this is two, and the other one is actually the equation that we got from the Maxwell construction. Here, this is equal to P ec, right? B gas minus B L. And this is the third equation, right? So plugging, okay, so I'm not going to do the full algebra here. I'm just going to show you how this equation, like you just have to do substitution in, like you can, for example, take BL and PQ here and plug them here and just get the gas, and then take that value for the molar volume of the gas and plug it in this equation. And then you will have the solution. And the full relation, it's something with a lot of terms. And this would be the solution. Notice that there is no dependence on the equilibrium pressure. So whenever you want to find B of J, you can find it knowing B of the liquid. Okay. I know it's a very hard expression to write in, but the important thing actually is that you can have an expression. You can construct the function that you can see on experiments. Okay. So let's move on and do. Do you have any questions of anything? Any of the steps? No. So let's move on to the equation, to the example of the exam. The example, it's a very nice example because we are going to see how you can understand a spring that breaks using phase transitions. on one side of the transition the spring is connected, and in the other side it breaks. So it actually behaves differently. So the question is, suppose that we have a mass like a spring, with some length. Okay. And the spring, and then it breaks. Before the breaking, the free energy density, the free energy density is given by this expression. So, do you recognize this expression? Okay, so this is just the energy of a spring in general. And, okay, this is the mass of the spring. The mass, this is the mass distribution, okay? Here, F is the free energy. And after, the free energy density is described by this expression, okay? Here, K is bigger than H. C is bigger than 0. And XO is bigger than 0. Okay? The first thing they asked from us is to find the tension. And B, find critical. And the second thing that they asked us is find the critical chemical potential. And lastly, for for any temperature, they will give us a temperature. We have to find the tension in order to bring the spring, okay? That's the three things that we are required to do. Okay? So the first thing, we see that they asked us the tension in terms of temperature and length. Okay? So generally we know. Okay, so why here it's temperature and not entropy? If we don't have, if we have temperature and not entropy, we don't use the internal energy. We use something different, right? Exactly. Perfect. The Helmholtz free energy. Okay, so this would be the differential of the Helmholtz free energy. Here, the conjugate variable of the tension is the length, right? And here, instead of having number of particles, we have the mass, which they relate with each other. But here we have since there are not particles, it's a spring. Then we have the mass per length. Okay. Like this is the mass density. Okay, it's mass over length. Okay. So, knowing that this is an exact differential, we can use Euler's criterion, right? And just say that this is the Okay, so for small lengths, then the free energy is given by 1 over 2 m. Okay. So since x is a density of mass, how many mass I'm going to find in some length? Like for how many mass I'm going to have some length. So then I just plug in, I don't know if I have this, x is just L over m. Okay, this is what I mean. So I just perform the derivative with respect to L, right? Which is the formula that I have, and I got this expression. And for B, like after doing a hard enough elongation, this is the free energy that I'm getting. So I just plug the definition of x here on the free energy and just perform the derivative. Okay? And I got these two expressions. Okay? So that's how we find this is A. How would you find mu?
Wait, what is H?
H. Ah, sorry. Here, there's this H. Sorry, it's a constant after you broke the spring. Okay. Well, it's constant with respect to length, but it can be a function of temperature, right? Okay. How would you do the second exercise? The second question. just as the tension is a derivative from the free energy, right? The chemical potential is also a derivative of the free energy, but with respect with who? In this case, the mass is the conjugate variable, right? So again, so this would be the expression for the chemical potential. Right? Or we can, you see that this is very similar to this, right? We can relate them, we can relate the tension. Because this is actually just with x squared, and so if we divide by this k, then we have the first exactly the same thing. And for big lengths,
אני מפריע פה?
כן.
שאתם...
כן.
בתרגול.
אמור להיות פיזיקה עוד רגע.
בעוד רבע שעה.
עוד
עדיין יש לנו את התרגול.
כן, עוד רבע שעה.
מצטערים. אז אני הולך להניח את התיק שלי פה. סליחה.
Okay, so we have just to perform this derivative, right? So just as I did here, you change from x to m to n over m, and you perform the derivative, you will get something like XO. And again, we can convert this into the, like with the free energy. So this is these are the two muons. And why do we care to convert them to the free energy? Because as we saw at the beginning, on the phase transition, both free energies are the same. So we can have actually an expression for on the terms of the like this for the tension, and then we can equate this and find the tension for the transition, right? In terms like using the chemical potential. Okay. So we find the chemical potential for both phases, and then like we have to equate them to say that this mu is the same as this mu, and when that happens as a function of tension, we have the phase transition. Okay, and the last thing is that we want to find for all the temperatures the tension that breaks the spring. So how do we do that? Exactly as I told you, we have to find the phase transition, right? Which is by equating the mu's. Okay? Like we have to do this, we apply this condition. Okay? So this is F1. So both of them come with a minus sign, so I'm going to just get rid of that. So also this is what happens. Exactly, perfect. So then I can erase this index, right? Then I can move this to the other side. So I can erase this, I can divide both sides by this, and this would be the equation. And finally I can solve for the tension, and the tension is given by 2k of t, h of t, and as you can see, and this would be the expression, and this depends on the temperature by the constants of the spring, right? And this will be the result. This is like, so this will be the tension at any temperature that we want. We just plug into these functions, and we get the tension to break the spring. Okay. Any questions? Anything?
Why here you didn't need to use the second derivative?
Okay, sometimes it's useful when I have this curve and I have a state equation, right? But in this time I don't have this state equation. I have the equation for the energy, right?
Yes.
Here. So instead of using the state, some equation given for this material, I just can derive everything using the conditions that we saw last class of equilibrium. And
Also here the second derivative is larger, is 0.
like if we would get like this is some sort, okay, so this is an expression, state equation, right? So then we will have to meet all those conditions of stability again. But actually the exercise was to derive that equation, okay?
Okay.
We wanted to find it. After that we can do some things.
Okay.
But we can use other conditions just to arrive and get the state equation. Okay?